Hi, I will now show you Lévy's upper theorem about observations of a random variable. Let xi be a random variable in L1 and define mn as the expected value of xi given fn, where fn as usual is thought to be the nth member of a filtration. Okay, so now the setup is slightly different as before. I am not starting with a Martingale, I'm starting just one single random variable, and I imagine these as the expected values of my random variables conditioned on some pieces of information I know up to time n. So there is some process in the background, there are some happenings, events in time in background, and given anything I know up to time n, I'm making a conditional expectation, a best guess of my random variable xi, which might not be, of course, fn measurable. Maybe it lives in the far future, and that is going to be mn. Okay, and I also want to define another quantity eta, which is going to be the expectation of xi given f infinity. Remember, f infinity is the sigma algebra generated by all of the fn's, the union of the fn's. So that's thought to contain all information I can observe up to infinite times. Now the theorem is that mn is a uniformly integrable Martingale, and therefore it converges, and its limit is eta. Almost surely. That's the theorem. Okay, not only almost surely, actually also, I forgot to add, also in L1. Okay, so that's Lévy's upper theorem. So if you have a random variable which has a finite mean, and you think about this as guessing its mean. You're guessing its mean based on what you've seen up to time n, and that's the mean based on what you can ever see. If you collected all of the information you can, that's what you have. Then this is a Martingale that converges to eta almost surely, and in L1. That's the theorem. Okay, the proof will consist of 3 steps, and it's gonna be a bit longish. First, that it's a Martingale is trivial. That M is a Martingale, that's trivial. Okay, when we introduce Martingales, then this was one of the examples, that the conditional expectation of xi according to a filtration, that's a Martingale. It follows easily from the Tower rule, so I'm not going to explain that more. The second thing I want to do is uniform integrability. So second, I want to show that M is uniformly integrable. Okay, that's not so trivial. So let's do that. All right. Now recall that we had a lemma about if I can find it, about these tail kind of expectations. So if you have any random variable in L1, then for every positive epsilon you can fix a k, so that I want to use lemma 1. So if you have a positive epsilon with an L1 random variable, then there is a delta, so that whenever you have an event smaller than delta in probability, then you have expectation of x under that event less than epsilon. That's a lemma I want to use. Okay, I want to apply this lemma on xi, on this guy here. So let's just write this out. Okay, so first I want to start with fixing an epsilon. Fix an epsilon, and then by this lemma I can pick delta positive, such that whenever probability of f for any event f, whenever the probability is less than delta, it follows that the expectation of mod xi on this f is less than epsilon, and this is for any event f that has probability less than delta. This follows. Okay, so let's fix that, and also fix, once all of this is done, fix also k that's larger than e of psi under the mod over this delta, which can be a huge number, but it's a finite number. Okay, so the first thing once these are fixed is to find an L1 bound. So let's start looking at Mn mod. Okay, by definition I'm looking at the expectation of psi given Fn mod of the expectation, of this conditional expectation, apply a Jensen on the conditional expectation and the convex function mod, so that's smaller than or equal to if I bring the mod inside the expectation. So that's a mod conditioned on Fn. Okay, this is true almost surely. Everything here, whenever I say conditional expectation, everything is almost sure. And now I'm going to apply an expectation on this chain of inequalities. So I'm going to do E of Mn mod less than or equal to E of mod psi given Fn. And now by the Tower rule I can collapse this into the expectation of mod psi, which is of course finite. So I have boundedness in L1 already, which is good, but I have more. One thing I want to do is look at the probability that Mn mod is larger than k. Apply a Markov on this. Apply a Markov on this. Expectation of mod Mn over k, and apply the previous observation here. That's bounded by E of mod psi over k, and the way we fixed k is that mod psi over k is going to be less than delta. Just rearranging this, that's less than delta. Okay, so we have this kind of uniform tail bound on the Mn, and now we can prove uniform integrability by combining all of these together. Okay, so let's look at the expectation of Mn mod under the event Mn mod is at least k. We want to show that if I take a supremum on this in n and then take k to infinity, then this goes to 0. So I want to show actually that I can make this smaller than epsilon uniformly across all n's by this big enough peaking of k. Okay, so let's put in the definition. Expectation of, so what is Mn? Mn is the expectation of psi given Fn. That was the definition we made on the event that Mn is larger than k. Alright, all I did was just plugged in here for Mn, I was plugging in expectation of psi given Fn, which was the definition we started with. Alright, now apply Jensen again the same way as before. Jensen on the conditional expectation, bring in the mod for psi. That makes everything smaller than or equal. The indicator is non-negative, so that's fine. So this is smaller than or equal to the expectation of mod of psi given Fn. Okay, so what happened was that this mod from out here went onto the psi by Jensen inequality. Add in the same event Mn larger than k. Okay. Now this guy here is Fn measurable. This event is in Fn because the Martingale is adaptive. So whatever it does, it's Fn measurable. And therefore, I can actually bring this event in and out this conditional expectation. If it's Fn measurable, then it can go in and out the conditional expectation. So that's my next step. I'm going to bring it in. Expectation of, and then mod of psi. Then I'm bringing this event in, because it's Fn measurable, so I can bring it in the conditional expectation. All of this is under the conditional expectation given Fn, and then I have an outer expectation on this. Okay, of course now at this point I can apply a Tauber rule. I can collapse the two expectations and just write expectation of mod psi on the event mn larger than k without any conditioning anymore, because the Tauber rule collapses the conditional expectation with the outer expectation, just giving me a full expectation. Now if I call this an event f, if I now call this an event f the same way as I had event f up here, if I do that, then as soon as I have the probability of these events more than delta, I know that this whole business is smaller than epsilon. But now if you look at the line above, it's exactly, the things are exactly set up in a way that this probability is smaller than delta. So the probability of this f here is smaller than delta, therefore expectation of psi mod under that event f is smaller than delta, smaller than epsilon. So that whole thing is smaller than epsilon, and that proves uniform integrability, because if I look at expectation of mn under the event mn larger than k, by this chain is smaller than epsilon for every n at the same time, just by picking k large enough. Okay, so that proves uniform integrability. Now there is one more step I need to do, one more sequence of proof I need to do. I need to show that the limit of mn is actually eta. So from uniform integrability, if I go back to the previous statement, then I know that for uniform integrable martingales I have a limit, and moreover I also know that mn can be obtained as e of m infinity given fn. What I need to now show is that in this particular case the limit m infinity, so I need to show that the limit m infinity, which I know by the previous theorem, is actually, this limit here is actually equal to that guy there, this eta. So that's another thing I need to show. I know from uniform integrability that I have a limit, but I don't yet know that this limit is actually eta. So that's the third step to do. Okay, so let's do that. Okay. So number 3, show that the limit m infinity, which I know exists by uniform integrability, is equal to eta, almost surely. Okay, and I also know, so from the previous theorem, I know that I have almost sure limit, and I know that I have L1 limit. So once I identify the limit, then I will finish proving almost sure and L1 convergence. I just need to know that this convergence actually happens to this eta there. So I need to show that those are equal. Okay, I'm going to show this. For psi positive. If that's not the case, homework, work out the details. And here is the way I'm going to do this. So it's going to be quite an involved and a little bit funny proof. I'm going to start with picking any event in f infinity. So f infinity is the sigma algebra generated by the union of the fn's. And I'm going to define two measures on f. One of them is going to be the expected value of eta on the event f. So if you fix eta, which is fixed to be the expectation of psi given f infinity, if you fix eta, then plugging in any event f here will just give you some number back, and that's going to be, it's actually a measure. You can check that this is a measure. And I'm going to define another measure, q2 of f, which is the same thing with, is the same definition, except I'm using m infinity, the limit of the Martingales, which I know exists. Everything here is almost true. Okay, now here is a calculation which is going to be a bit funny. If f happens to be in Fn, which is a subset, of course, of f infinity, if f happens to be on Fn, then let's just do a quick calculation on these measures. So q1 of f is what? It's expectation of eta on f, which is what? It's expectation of, so what was the definition of eta? It was psi given f infinity, psi given f infinity on f. Okay, so this guy here was eta. Okay, now f is in Fn, which is a subset of f infinity, so f is actually f infinity measurable, so I can bring that f inside the conditional expectation. Let's do that. Expectation of psi on f, and then given f infinity. Okay, now that is going to be a Tower rule now. Expectation of the conditional expectation is just ordinary expectation, so Tower rule tells me that this is psi on f under just a single expectation. Okay, so now I'm gonna do the same with Fn. So I'm gonna do all these steps backwards with Fn. So take the expectation and write this according to the Tower rule as expectation given Fn and then an outer expectation of that. Okay, just the Tower rule again applied to Fn this time rather than f infinity. Okay, so I assume that f is Fn measurable, so this goes in and out the conditional expectation. So let's do the conditional expectation of psi given Fn only, and let's bring out f from that conditional expectation. It's still, oops, this is a conditional, f is still of course inside the outer expectation, so I can't pull that out from there, but I can pull it out from the conditional expectation. Now this guy was my definition of the Martingale. So what I have now is expectation of mn under the event f. Okay, now comes the previous theorem, which tells me that mn for a uniformly integrable Martingale, where is the previous theorem? For a uniformly integrable Martingale, mn is exactly expectation of m infinity given Fn, and I already have uniform integrability, so I'm going to put that in, that mn is the expectation of m infinity given Fn. So I'm putting this thing here for mn. Alright, and the next step is again I can bring f in and out the conditional expectations, so I'm going to bring f inside the conditional because f is Fn measurable, so it behaves like a constant under the conditional expectation. So it's going to be m infinity on the event f under the expectation. I can collapse the expectations now according to the Tower rule, so I end up with this. And if you look up here, what you find is that is the same as q2 of f. So what did we learn from here? What did we learn from here is that q1 is the same as Q2 on the sigma algebra Fn, and this is true for every n. So in fact Q1 is the same as Q2 on the union of the Fn's, which means that in fact Q1 is the same as Q2 on F infinity, because F infinity is generated by this union. So these two measures are actually the same for any F infinity set. Notice that the following event, eta larger than M infinity, is actually in F infinity. Okay? Why is that? Because M infinity is the limit of the mn's, so it's F infinity measurable, and eta is done as a conditional expectation. Eta is done as a conditional expectation of psi given F infinity, so that's also F infinity measurable. Both of these guys are F infinity measurable. So therefore, this event is in F infinity. So, if this event is in F infinity, then Q1 is equal to Q2 on this event. So let's apply Q1 and Q2 on this event. Okay. 0 is the difference of Q1 on this event and Q2 on this event, because they are equal. But what is this? So what is Q1? Q1 is expectation of eta on this event, eta larger M infinity, and Q2 is the expectation of M infinity on the same event, so I can immediately collapse the two expectations and write this. Okay? And this thing is 0. This thing is 0. It follows from here, it follows from here that, I need a bit more space down there, it follows from here that eta cannot be larger than M infinity with any positive chance. So the probability that eta is larger than M infinity must be 0. It follows from the previous line. Why is that? Because if this would have a positive chance, then this indicator would be 1 in a positive measure of sets, and eta minus M infinity would be positive in a positive measure of sets, so this expectation could not be 0. Okay, the thing underneath here is never negative. Eta larger than M infinity is this indicator here. It makes sure that underneath this expectation I never have a negative thing. If the expectation is 0 of a non-negative random variable, then this non-negative random variable is 0 almost surely. In other words, this cannot happen almost surely. Or with probability 0 can it also only happen. Okay? And the same way, similarly, one shows that the probability of eta smaller than M infinity is also 0. And that together shows that M infinity is equal to eta almost surely, and that's exactly what we wanted to do. M infinity is eta almost surely.